So in this whole chapter, we've been talking about ratios and proportions, and those are a really big part of scale models and drawings. So we're going to focus today on finding dimensions of scale drawings and models, and also of actual objects. You know, who uses scale models and drawings? Video game designers are creating, scale models of people within a video game. Construction workers and architects maybe will create a scale model or drawing of a new store, a new roller coaster that they're going to build. And they can, use those models to kind of sell their idea. Construction workers have to bid on getting the job, so if you think about it, for our school construction, we probably saw some scale models, or maybe scale drawings at least, of what our school would look like. I also have a fun little clip to start us off on another example of where I've seen some scale models. So you probably have seen this movie. So in this movie we see a little scale model of, New York City. We also see a scale drawing of a Mona Lisa. So that movie is from Elf, or that clip is from Elf if you've seen it, but just another example of where we've seen models. So copy down your target and then we can get started. So a scale drawing is a two-dimensional drawing that accurately represents an object, and a scale model is a three-dimensional drawing that accurately represents an object. Both scale models and scale drawings are mathematically similar to the actual object. Similar. What does that mean? Well, we talked about this. Congruent figures are the same size, same shape. Similar figures are the same shape, but not necessarily the same size. So a scale gives the ratio of the dimensions in the drawing to the dimensions of the object. So scale is always going to be drawing to object. Or model to actual. That's how I like to name it. So know that. It's always going to be the drawing or the model to the actual. Here's an example of some scales. You'll be using this to create a scale. You could use it to create a scale drawing of maybe your house or a bedroom in your house, or a scale drawing of the United States. But the scale is going to give you what represents in the drawing to what it represents in the real life. So 1 unit in the drawing is 20 units in the real life, or 1 centimeter in the drawing is 1 meter in real life. So we can use proportions to find unknown scales or lengths. Let's look at this first example. The length of an object on a scale drawing is 2 centimeters, and its actual length is 8 meters. So drawing is 2 centimeters, actual is 8. Remember, we're always going to do drawing over actual. So let's write a ratio. We have the drawing being 2 centimeters, and it's 2, the actual being 8 meters. I want to fill in this blank. The scale is 1 centimeter to how many meters? That's what I'm trying to find. Well, again, remember, the scale is always given to you as drawing to actual, so you could set this equal to what you have. The drawing, in the drawing, 1 centimeter is equal to, I don't know how many meters, so this is what I'm trying to find. This is what I'm not sure about. But you really have a proportion now, and take a look. You could cross multiply, or you could also just use the multiplication method. What would you do to 2 to get to 1? Do the same thing to your denominators. Well, 2 divided by 1, or 2 times 1/2, 2 divided by 2, or times 1/2, will give me 1. So I'm going to do the same thing down here. Well, then 8 times 1/2 will give me 4. I can fill in that blank then. On the drawing, 1 centimeter is to 4 meters. All I did was take my ratio that they gave me and reduce it down to get this 1, and I found my 4. Let's look at another one. The length of an object on the scale drawing is 1.5 inches. The scale is 1 inch to 6 feet. What is the actual length? So this time I gave you the scale. If they give you the scale, I always start with that. Write it as a ratio. Label your scale first. Remember, it's always drawing or model to actual. So this one was talking about a drawing, so it's drawing to actual. Let's set that up in a ratio. 1 inch is to 6 feet. Now look at the other piece of information that they gave you. Well, the length of the object on the drawing was 1.5 inches. When you set this up, we're going to set this equal, again, it's drawing to actual. Over here, it's drawing to actual. You want to keep that symmetry. Well, the drawing was 1.5 inches, and what I'm trying to find is what is the actual length. So that's going to be my X down here. Also notice the units. If the tops are given in inches and this bottom here is given in feet, the bottom over here will be given in feet. So you really have that symmetry existing in this proportion. The tops match, the bottoms match. To solve a proportion, you can cross multiply or simplify. I'm going to cross multiply on this one. So I have 1 times x equals 1.5 times 6. So I have x equal to 9 feet. So the actual object would be 9 feet long if it was 1.5 long in the drawing. So remember that, a scale drawing, if it's smaller than the actual object, if the actual object is larger and you draw it down to be smaller, this is called a reduction. So if you were going to create a scale drawing of your house, that would be a reduction because you'd be shrinking your house down to fit it on paper. And then a scale drawing that is larger than the actual object is going to be called an enlargement. Think about this in science a lot. You may see scale models or models of cells and organisms, or when you look under a microscope, you're enlarging what you're looking at. So that would be an enlargement. So let's look at some of those real life examples. One where we're enlarging and one where we're shrinking it down. Under 1,000:1 microscope view, an amoeba appears to have a length of 8 millimeters. What is the actual length? Again, I always like to set it up as model over actual. And I already know this is what I don't have. So when I set up my proportion, my x is going to be on the actual. It doesn't matter which one. I'm going to put it over here. So my actual is what I'm finding. This is going to be my x. Look for a scale. A scale should be given to you somewhere. There is a scale in this problem, but I think this one's kind of sneaky. But where's the ratio? Remember, ratios can be written with these colons too. Here's your scale. The microscope makes something that's in the actual world size of 1 1,000 times its size. So the model is 1,000 times the actual being 1. This is your scale. They gave that to you. I need one more piece of information. It says under the microscope, so within the model or within the drawing, the amoeba appears to have a length of 8 millimeters. So that 8 goes on top there. Now you're ready to solve. Solve it just like you did with the other proportions. Cross multiply. 1,000 times x is equal to 8 times 1. And then divide to get x isolated and by itself. We can reduce this fraction, or we can use our calculator to get a decimal, or you can really just read it. 8 1,000ths, that's going to look like tenths, hundredths, thousandths. It's going to look like this. And don't forget your units. Since there were no units here on the scale, they're the same units, which means your units down on the bottom will be the same as its top. So it's millimeters. Another example would be something that maybe was smaller than the actual object. So under a microscope, you're looking at an enlargement, but this would be a reduction. Louis D'Astorino was the architect who designed Consol Energy Center, and while developing his plans, he made a model of the new arena using a scale of 1 inch to 48 inches. If the actual seats are 24 inches wide, how wide were the seats in the model? So try this one on your own. If you want to try it with me, you can work with me. If you want to pause and do it and then see if you've got it right, you can do that as well. Again, I always like to start with my scale, so look for the scale given to you in the problem. The scale of 1 inch to 48 inches. And I always set it up as model to actual. That's how the scale is given to you. So over here, it'll be model over actual as well. Well, what do we know? If the actual seats are 24 inches wide, so what do we know? We know the actual. The actual goes in the denominator, so 24 is going in the denominator. And what do I want to find? It says how wide were the seats in the model. So this is my x. Inches, inches, these are going to be inches, inches. Solve the proportion by cross multiplying. You get 48x equals 24 times 1, or 24. And to get x by itself, you divide by 48. So you get x to be a fraction. 24 divided by 48, that can reduce down. You could take out 12. And that would give me 2 over, oh, that's not 12, that's 2. 2 over 4, then you can take out a 2. Or you could use your calculator, but you're going to get 1/2, or 0.5 inches. So if you got that right, excellent job. The last part of this then is talking about a scale. Okay, so let's talk about these scale factors. A scale factor is a scale in which the units are the same, which means they cancel each other out. A scale factor is where the units are the same in a scale. Any scale can be converted to a scale factor, and look at how we do this. Here's your scale with units. We want to get rid of our units because a scale factor has the same units, which means they cancel each other out. So if we can get them both to be inches, then we can cross them out and get rid of them. Well, what did we actually do in this work right here? It's a conversion, just like you did in 7-3. So you would multiply by a conversion factor. You want to cancel out feet, so feet goes up top. You want to cancel out inches, so inches would go on the bottom. How are those two related? Well, 1 foot is equal to 12 inches. Now the feet are gone, and I'm left with my inches, and now my inches can be gone, and I'm left with a scale factor. So to get a scale factor, you're actually doing a conversion. If the object has been enlarged, the scale factor is greater than 1. If the object has been reduced, the scale factor is less than 1. And if the object has been preserved, which means it didn't change, what's left? Well, the scale factor must be equal to 1. So the last thing we're going to talk about today is checking the scale factor and see if it reduced or enlarged or preserved. So given the scale or the relationship, find the scale factor and then circle whether the scale reduces, enlarges, or preserves the actual object. Remember, to get the scale factor, you're canceling out your units. Start with your ratio. 2 inches over 1 yard. Cancel out those units. You're going to multiply by a conversion factor. Yards can be converted to feet. How are those related? Well, 1 yard is equal to 3 feet. Now that gets my yards to cancel, but I still didn't get rid of my units. You need another conversion factor here. So you're going to multiply by something else. In order to cancel feet, it would have to be on top. And I can convert feet to inches, which is what I want because I want to cancel these two. How are those two related? 1 foot is to 12 inches. Now the feet are gone, and actually so are the inches. Perfect. That's how you know you're done, when all the units cancel. And now you multiply straight across. 2 times 1 times 1 is 2. And 1 times 3 times 12 is 36. And then reduce this. So we can take out a 2 for both of those. Once it's reduced, you have your scale factor. It's 1 over 18. Does this reduce, enlarge, or preserve? Well, it's less than 1, so it reduces. Okay, pause the video, try the next two, then press play to check your results. So check your last two here. On B, we had 1 meter over 10 centimeters. To cancel these out, we multiply by centimeters and divide by meters. How are those two related? Well, 100 centimeters equals 1 meter. That cancels all my units out, and now you multiply straight across. 100 divided by 10 is 10. We can't reduce that anymore, so your scale factor is 10. If your scale factor is greater than 1, it is an enlargement, or it enlarges. And then the last one, make sure you set this one up with model or to actual. So you actually have 12 inches long for the tail, over 1 feet for the real cat's tail. And then you cancel out feet and inches. And you can see here that 12 inches to 1 foot, those are the same thing. So this actually just preserves the size. Great work.